Hi, everyone. Today, we're going to go over how to find out the volume of a tetrahedron, specifically a regular tetrahedron. Regular here just means that all the side lengths are the same length. So I'm calling them all S. In this problem on the homework, I believe S is given to you, but it can change from person to person. So I'm just going to solve this in general, and then you can plug in your value of S at the end. The most natural way to approach this problem is doing volume by cross-sectional area, which is to say, if I pick some height Z and look at a little horizontal slice here, well, I can integrate those areas as I go from the base of the tetrahedron all the way up to the top of the tetrahedron. And so what this looks like is, okay, volume equals the integral from 0 to h of the area of that red slice. Okay, so the main part of this problem is honestly just finding a formula for the area of the red slice. It's a whole lot of geometry, and it can take you a while if you don't know the right steps to take. So, okay, I've added some things to this drawing. The first thing I added was this line of, I think people call it a line of altitude. It's a straight vertical line dropped from the tip of the tetrahedron down to the base of the triangular bottom. At the bottom, it touches, I think it's called the orthocenter, the center of that base. And extending from that orthocenter, I've drawn two lines in purple, extending to two of the corners of the base. It'll become apparent why I've done that shortly. So what do we have to do? We are going to have to figure out, I put A's on here, maybe I should erase that for now. We are going to have to figure out a formula for the area of the red triangle, and that's going to depend on these side lengths. Okay, so the nice thing about a tetrahedron is any way I slice it horizontally, I'm going to get an equilateral triangle. So all the side lengths are going to be the same. I'm calling them A here. So if I can figure out a formula for A, presumably, which is only going to depend on, you know, S, sort of the side length of the tetrahedron, as well as the height above the base, Z, then I'll be good to go. Okay, so how do we do that? I'm going to start by finding a formula for H. Okay, so H is going to be calculated as follows. Scroll down a little. Okay, so H is tough, but you can get to H if you first start with these B's. So let's find a formula for B. Let's take this triangle right here and just pull it out and sketch it over here. So triangle looks like this. What you'll notice is this is actually sort of trisecting the base of the tetrahedron into three similar triangles. And so since it's trisecting it, you sort of know automatically this is a 120-degree angle, 360 divided by 3. So the others have to be 30 degrees. And okay, this side length is B, this side length is B, this side length is S, just from the diagram. And okay, there are a lot of ways to figure out a formula for B in terms of S. Perhaps the quickest way is the law of cosines, which most people forget after they see it, but it's like a fancy version of the Pythagorean theorem. It's going to tell you that this side length squared, so S squared, is the sum of the other two side lengths. Okay, and if this was a right triangle, I would stop, and that would be the Pythagorean theorem, but it's not a right triangle, so you have to correct for that by subtracting 2 times, okay, one side length times the other, times the cosine of the angle between them. which we just said was 120 degrees. Okay, the reason this is the Pythagorean theorem is if this was 90, cosine of 90 degrees is 0. So the whole last term would fall out. But it's not a right triangle. Cosine of 120 is actually negative a half. So this looks like that's negative 2b squared times negative a half. And okay, that all works out to be b squared plus b squared plus b squared. So 3b squared. I said I wanted an equation for b in terms of s. I think I can get away by just solving for b squared in terms of s. Of course, you can take a square root if you want to. I think we can get away with not doing that. Okay, so I said the first step to finding a formula for the height h was finding a formula for b, so I've done that. How am I going to connect this to the height of the tetrahedron? Well, you just stare at it for a second and you think, okay, height here, base here, and then the side length, that actually forms a right triangle. Convince yourself it actually is. But yeah, it's a right triangle. And so taking that triangle out, I can write another formula down. This one I can just use straight up Pythagorean theorem for, and I want to solve for h. So what do I know? I know that h squared is the hypotenuse squared minus the other side squared. And I know what b squared is, right? B squared is right above me. That's s squared over 3, just from right here. Okay, so simplifying, this is 2/3 s squared. And then, okay, I do need to solve just for h, so let's actually take the square root this time. So I get 2/3 s. If you're really on top of it, you might say, okay, I'm taking the square root of s squared. Shouldn't that be the absolute value of s? But s is the side length, so it's always going to be positive, so I can just write s. Okay, so I have a formula for h in terms of s. That's going to be really valuable. And actually, I'll highlight this right now. You can take this and go up to your volume formula and say that's going to be my upper bound of integration, because if you think about what we're integrating, we're starting by, the first slice in a sense is the base, and then we go up and eventually we get to here, and then we slice it more and more, and then eventually we get to height h. So that is our upper bound of integration. You can plug that in now if you want to. But then the other question is, okay, how do I finish up and get this formula for the area? Okay, and this is a little bit tricky. The thing to think about is, first of all, to make note that this triangle and the base of the triangle, or the base of the tetrahedron, are similar. And actually, like any triangle I want to draw on here is going to end up similar to another triangle. So if I look at this one, and I look at the whole face of this tetrahedron, those are similar triangles. And whenever you see similar triangles, you can set up ratios between their side lengths, right? So what I could do is I could say, okay, my goal is to figure out A, right? Because if I find the side length of the red triangle, I can find the area, and that's our whole goal. So I want to find A. A is going to correspond to S down here. And then what other component do I want to use? Well, you could pick a lot of things. But let's say I, want to involve H in my ratio as well. And so what I'm going to do is I'm going to say, okay, the ratio of A to S is the same as the ratio of this portion of the altitude to the entire altitude. Okay, that's a valid thing I can do. So writing that as a formula, maybe I'll just put it right here. A is to S as, well, what is this altitude, the distance from the top of the tetrahedron to that red triangle? Well, if the full distance is h and this distance is z, then it's just h minus z. So h minus z over the full height, right? So that's my ratio that I set up. I can take this and then solve for a. This is h minus z over h times s. And okay, maybe I simplify a little bit and I say that's, okay, h over h is 1 minus z over h times s. And okay, I know what h is. So I can also take this, plug it in here. So we want as few variables floating around as we can. It's 1 minus z over square root of 2/3 times s. And we have an s on the outside. And okay, let's actually distribute the s through. I get s minus, I suppose the s's would cancel for the second term. Just be left with z over that square root. If I don't want the square root in the bottom, I guess I could flip it and it would look like 3/2 times z. Okay, so that's my formula for the side length of this specific triangle here at height z. So it's good to see it depends on z and it depends on s. It's as good as I can get. And then I said, okay, our last step is, once I know the side length, I can find the area. I won't bore you with the details of that. You can say, okay, if I have any equilateral triangle, you can do some geometry. I'll let you guys figure out the details if you want. But the area here, so I'll call this A of z, in general is going to be, what's the formula for an equilateral? I think it's √3/4 times the side length squared. And so all we need to do, let me just grab this and pull it up. All we need to do is plug that in here. Right, we know what A is, so let's plug it in. All of a sudden my area formula becomes √3/4 times s minus, so it's pretty ugly, that times z, whole thing squared. Maybe I'll just put this down here. Okay, and yeah, that is our formula. And this is what we're going to take. I'll actually just cut and paste it up here. That's exactly what we were looking for when we started this whole thing off. We wanted some nice area formula. Well, maybe not so nice area formula that we can just plug right into the volume formula. So similarly, take this, plug it in here, and okay, depending on your particular choice of s, you should be able to integrate this thing and get a number out. So yeah, there you go. That's like 90% of the hard work done. I hope this helps. And yeah, good luck.